In Chapter 10, Section 2, we're going to expand upon what we did. We had rational exponents. Now we're going to go higher in the number category from rational number to real numbers, which includes the irrational numbers exponents as well. We're still pursuing state standard number 12 for Algebra 2. Here's our objectives for this lesson. What we would like to do is make sure we can simplify expressions involving irrational exponents, not just fraction exponents, but irrationals. Solve exponential equations, and we need to define and graph exponential functions. So we're not done with graphing just yet. All right, and what we need is since yesterday in our previous lesson we reminded you all those property of exponents, I'm not going to show them again today, but you will need to remember them in order to apply that to this material as well. So let's look at our first situation involving irrational exponents. Square root of 2 is my exponent. And before you get all worried about it, let's remember our property of exponents. These bases are both 6. We are dividing. So the property says if you are dividing and the bases are the same, keep the base, subtract the exponent's numerator minus denominator. So that's 6 to the square root of 2 minus negative the square root of 2 power. Don't forget, subtracting a negative is adding a positive. So this is the square root of 2 plus the square root of 2. That tells me I've got 6 to the 2 square roots of 2 power. Now, let's go backwards in our property of exponents, because we said in our previous lesson you got to know them forwards and backwards. So we could think of 6 squared to the square root of 2 power as 6 times to the 2 square root of 2 power if we go backwards versus forwards. So let's rewrite 6 to the 2 square root of 2 power as 6 squared to the square root of 2 power. From there, 6 squared is 36. That's as far as we can solve that. And for right now, we're going to leave this as an exact answer, square root of 36 to the square root of 2. Later, we could approximate that using our calculators. But in this example, we're going to stick to our exact answers. Talk about real number exponents. What's more of a real number than having pi as an exponent? So I've got 4 to the pi power times 2 to the 3 minus 2 pi power. I would suggest that I see 4 and I see 2, and I realize that they are both powers of 2. So let's write 4 as 2 squared. And now when I have a base raised to a power, that's raised to a power. We're going to keep the base and multiply the exponents. 2 times pi is 2 pi. I'm ready for my next step in my properties of exponents. I'm multiplying. The bases are the same. I'm going to keep the base and add the exponents 2 pi plus the binomial exponent 3 minus 2 pi. As I do that, 2 pi plus negative 2 pi drop out, and I'm just left with 2 to the 3rd power, and 2 to the 3rd power very simply is 8. All right, let's look at another one involving irrational exponents. I've got 3 raised to the 2 square root of 2 power, and that entire expression is in turn raised to the square root of 2 power. Again, a base raised to a power, you multiply your powers. And the square root of 2 times the square root of 2 is the square root of 4, or 2, times this 2 leaves me with 3 to the 2 times 2 power, and that's 3 to the 4th power. 3 times itself 4 times is 81. All right, let's get into the solving the exponential equations portion. Here's our strategy. For now, until we learn logarithms, we want to express each side of the equation as a power of the same base. Then, if the bases are the same, we can set the exponents equal to each other and we can solve. Important last warning here, we need to check our answer. It's just not a thing that we're saying check your answer to make sure it's correct. We're saying, when we say check your answer, we're also saying watch out for extraneous roots. So let's look at this one. And 4 and 8 look like they're powers of 2, so let's see if we can rewrite that. So 8 is 2 to the 3rd power, 4 is 2 to the 2nd power, but I have 1 over 2 to the 2nd power. Well, let's try to make that just a power of 2 and say that's 2 to the negative 2nd power, because the negative exponent means take the reciprocal. On the left, a base raised to a power raised to a power. We multiply those powers, that's 2 to the 3x. Now, this is logic. So let's think clearly about this. If the left side is equal to the right side, and the bases are both the same, the bases are both 2, the only way this can be true is if the exponents are also equal to each other. So 3x must be the same as negative 2. And if we solve that equation by dividing for 3, we find out that x is negative 2/3. So for now, this is how we're going to solve exponential equations. When we learn logarithms, we'll be able to address the situation, because some of you may already be thinking, what if I can't express both sides as the same base to some power? And that's what we need to look at when we get to logarithms. All right, let's do another example. In this case, I've got 5 to the 4 minus t power. That equals 25 to the t minus 1 power. And let's call 25 5 squared, so we both have powers of 5. On the right, a base raised to a power raised to a power. We multiply those, so that's 2t minus 2 when we distribute that out. The only way that this equation can be equal, if the bases are equal, the exponents must also be equal. So 4 minus t must equal 2t minus 2. Solve that simple equation, so let's add t to both sides. Let's add 2 to both sides. Let's divide both sides by 3, and t is equal to 2. All right, next thing we want to look at is an exponential function. Exponential function. Not just solving an exponential equation, it's a function because we have two variables here, x and y. And let's read the fine print. B must be greater than 0, b cannot be 1. The function divided by y equals b to the x power is called an exponential function, and of course b is the base, x is the exponent. So y equals 2 to the x power. We want to graph that. Best way to do that is to start with a chart of points. And I suggest we have some negative values, we have 0, we have some positive values, and see what happens. So let's substitute in negative 2 for x. 2 to the negative 2 power, that's 1 over 2 squared, or 1/4. Let's substitute in negative 1. 2 to the negative 1 power, that says take the reciprocal, so that's 1/2. Let's try 0. 2 to the 0 power, anything to the 0 power is 1. Let's try 1. 2 to the first power is 2. Let's try 2. 2 squared is 4. If we substitute in 3, 2 cubed is 8. We can keep going, but that's enough to get the idea for this particular graph. So let's get some graph paper going, and let's start plotting the points. So there's the point negative 2 1/4. There's the point negative 1 1/2. Here's the point 0 1. Here's the point 1 2. Here's the point 2 4. And the point 3 8 is a little bit off my graph. So as I connect the dots, an exponential function is going to have a curve kind of shape. And in this case, we can think of the x-axis here as an asymptote. It's not a hyperbola, so don't confuse that. But we can think of it like one. It's actually approaching a limit. It's getting closer and closer and closer as we go to the left here in this particular case. But it's never going to cross, never going to touch, never going to get parallel to the x-axis in this situation. So this is what the graph of an exponential function looks like. Basically, we'll be graphing several of these. The only difference is the base will change. Instead of 2, it might be 3, it might be 5, it might be 8, it might be 10. And as we look at this graph, we tell two things about it. One, it passes the vertical line test, which remember meant imagine every conceivable vertical line. If it hits that graph at only one place, it's a function. That was a long time ago we discussed this. And let's go one further. Think of every conceivable horizontal line. If every conceivable horizontal line hits it at only one point, and I know that's difficult to conceive out here, but it is true. If it only intersects this graph at one point, Not only is it a function, but it's a one-to-one function. So it passes the vertical line test, it passes the horizontal line test. That's a one-to-one function. That's our look at real number exponents, exponential equations, and exponential function graphs.